The process we've just outlined can be taken to be a pretty good plausibility argument for the idea that if we're given a differential equation with an initial condition, a second order differential equation of the type we've been looking at, where the coefficients of y double prime, y prime, and y are all functions of t, which are defined and in some cases non-zero, we can always get a solution in the neighborhood of the initial point. Now, our geometric interpretation of this is that we have a point t naught y naught on a solution curve, and this is our initial condition, that we have this point and that y prime of t naught has some value v naught, which is indicated by a slope. Then the equation a of t y double prime plus b of t y prime plus c of t y equals 0 has a solution on an interval alpha less than t less than beta, with the interval containing t naught provided a of t, b of t, c of t are defined for all t in the interval, and a of t is not 0 for all t in the interval. As we've seen, the key step in constructing a solution curve is to be able to evaluate y double prime at one point, then at the next point, and so forth. And evaluating y double prime depends on being able to solve this equation for y double prime. Remember that we assume that we know all of the other quantities that go into this equation for a given point, and that when we solve for y double prime, we actually get a solution. And that requires that the a, b, and c functions all be defined at the point, and also that the a of t function be non-zero, because in solving for y double prime we have to divide by the value of a of t. So I'll say, if it's so, then a of t y double prime plus b of t y prime plus c of t y equals 0 can always be solved